here to talk about the security in Ethereum and its ecosystem. And while everyone around is focusing more on how great Ethereum is and how perfect its ecosystem is, I would like to highlight the problems that we currently have. Because, in my opinion, solving problems is even more important than advertising and telling everyone around about your project. And I'd like to start with a small introduction, which I'm not often doing. So, first of all, I'm a co-founder of Ethereum Classic, the original chain of Ethereum that was created in 2016 when, after the DAO hack that caused Ethereum users to lose quite a lot of money, if the hard fork would not have happened and this chain would not have been created, this money would stay with the DAO hacker, but Ethereum split it in two chains, one of which is supported by Ethereum Foundation nowadays, and the other one was supported by the community of Ethereum Classic. And I have created one of the core teams that was doing it in the early days. It's called Ethereum Commonwealth, and you can still find it on the Ethereum Classic team section. Also, I have some experience in security. I'm a hacker, and I have designed and executed one of the most impactful consensus-level attacks in our industry. In 2019, I have exploited a vulnerability in EOS network consensus, which was a top 7 chain of its time, and I froze its mainnet for a month. And right now, I'm a blockchain validator on EOS top 30, so if you have any EOS by any chance, you can proxy to our vault, DEX223 block producer. Also, I have designed a 51% attack solutions called the amendments to Nakamoto consensus. This is a method of addressing proof of work related attacks in the proof of work chains, obviously. So there is my security background. And I would like to start with general conception of security. Everyone around is talking about security and how important it is, but security actually is a complex set of processes and rules which actually have a goal. And in different areas, the goal of security can be different. And in military, for example, the security is mostly focused on concealing your technology from your potential enemies. And in banking, the privacy of users may be more important than in any other area. And in blockchain, we are mostly dealing with money. And since we have automated projects and automated programs like smart contracts, we need to make sure that there are as few possibilities for users to lose their money as possible. And so in blockchain, the security is mostly focused on protecting our users from losing money. So here are some basic security principles. Normally there are 7, but I would like to add the first one: nothing is absolutely secure. And this principle means that no matter how good your security processes are, how hard you are following the best practices, and how much security audits there were, you can never guarantee that there will be no vulnerabilities and nothing bad will ever happen to your software. So you have to be prepared to deal with something that can happen in a wrong way or with some vulnerabilities that will still happen. The second principle is the principle of fail-safe defaults, which means that you actually have to design your software in such a way that its default behavior will restrict some operations which can potentially cause some damage. There is access restriction, separation of duties, minimize attack opportunities, complete mediation. Those principles, you can find them on the internet, and they are not that much important for us in the context of our today's discussion. But the error handling is important. It actually means that you have to deal with software errors that can occur during the execution process. And secure by design principle. It actually means that you cannot delegate responsibility for delivering secure software on someone who will be interacting with the software. So you can build an insecure piece of code and write a guideline how to interact with your insecure code in a way that will not cause any damage and pretend that it will work. No, it will not. So I would like to start with a statement that we have an ERC20 standard in Ethereum that everyone is using right now for like 9 years. And this standard violates two of the security principles that I highlighted on the previous slide. The principle of fail-safe defaults and the error handling. With ERC20 standard, the error handling is impossible in some cases, and it can cause potential loss of money. And we have built a script that calculates the amount of money that was lost since the disclosure of this issue. And there were $90 million lost on 1st November 2024. And on 10th November, another user lost $25 million. So right now, this value is $115 million. Here is the QR code. If you are interested in this script, you can find it here. Now I would like to explain this issue in a little bit more details. And the issue is that in ERC20 standard, it is designed in such a way that when you are transferring your tokens to addresses and to smart contracts, it must work differently. But there are two methods of transferring tokens in ERC20. One is designed to deposit tokens to smart contracts, and another one is general purpose. And the general purpose transferring method can still deposit tokens to smart contracts, but it is doing it in such a way that if the contract is not designed to receive such tokens, then instead of an error that can prevent this accidental deposit, the tokens are lost, and the user have no possibility to recover the financial assets that he has sent to a smart contract. So I would like to dive into the history of this problem and explain how this happened. The ERC20 standard was created in 2015. This was quite an early day of Ethereum, and there was a cold stack depth bug in the EVM. I don't want to dive into details of what was this bug, but this bug made it impossible to safely call one smart contract from another smart contract. So the developers of the ERC20 standard, they faced a challenge of inventing some method that would allow tokens to be deposited to smart contracts. And they came up with an idea of creating two different methods. The transfer function, which resembles a push transfer method. You are just sending tokens from your address A to some address B, and the address B receives your tokens. And the approval and the transfer from pattern. This pattern is designed to deposit tokens to smart contracts. So instead of transferring tokens with the push method, you allow the address B to withdraw tokens from your balance. Then you call the function in token B, in the contract B address, and the tokens are pulled from your address into the contract B. As a result, we have two different methods, one of which is not designed to deposit tokens to smart contracts. The push transferring method is not designed for this, but this is not anyhow restricted by the standard, and a user can still call this function, and in some cases, it is 100% possible to identify if the receiving contract is designed to deal with tokens. And even if it is not, there is no error, and the money is lost. In 2016, the cold stack depth bug was fixed in Tangerine Whistle hard fork. So this issue does not exist anymore. And we don't need the approve and transfer from method, basically, because if there would be a method of transferring tokens with a push method that would allow this transaction to be handled on the recipient's end, then we will not need a special method of depositing tokens to smart contracts. with the pool method. And this is exactly how NFTs work nowadays. For example, the ERC-721 NFT standard is built in this way, and the native currency of Ethereum is built in this way. You can't lose your Ethereum if you will send it to some smart contract which is not designed to receive it. The contract has to declare explicitly that it is designed to receive Ether by implementing a special function which will declare it. And in NFT, it works the same way. And in 2017, there was an ERC-223 token standard, which was created to solve this exact problem of lost money. And the ERC-223 tokens work exactly the same as the native currency of Ethereum and basically any EVM compatible chain. They only implement the push transferring method with transaction handling. In 2017, the security issue related to ERC-20 transferring patterns was disclosed to Ethereum Foundation, and it was highlighted that $16,000 were lost at that moment. In 2023, the ERC-20 security issue was still unpatched, and it cost $60 million lost. As of right now, there are $115 million lost because of this issue. It is still not fixed, even though it was reported 7 years ago. Here is the report. And you can still find it on their GitHub page. And now I would like to switch to the description of the processes that surround it and which resulted in the situation that we have right now. So this is the EIP lifecycle scheme described by EIP-1. So the EIP is submitted in draft status, then it goes to review, last call, or final. And here is the description of the last call status, which is important for us right now. Last call. This is the final review window for an EIP before moving to final. This lasts 14 days. I would like to describe the EIP process in a little bit more of details. So EIP is basically Ethereum improvement proposals. Anyone can submit a proposal, and it can become a standard or informational issue or some modification to how Ethereum or Ethereum ecosystem works. And there is a rule among EIP editors that EIPs in draft and review status are not recommended to be used in production. There is another rule that the final EIPs are immutable, and there is no way to add any description of any problems to the final EIPs, which leaves us with a process where in this stage, the EIP is never used in production. And in this stage, there is no way to add any security considerations to the description of any EIP. This leaves us with 14 days time window to discover, describe, and report any security issues. And anyone who wrote any line of code himself understands that this is completely impossible to identify and report all the security issues within this small time frame. And software issues can be discovered at any stage of software development lifecycle, not only during the development stage. And there are some precedents where software issues were reported many years after the production implementation of the software. So the EIP process is completely unsuitable for discovering and dealing with security issues discovered in EIPs. In 2023, a proposal was submitted to the EIP editors that focused this exact problem of the EIP process. And it was proposed to make security considerations section of EIPs append only, so that it would be possible to add security considerations to final EIPs after they were finalized. However, EIP editors had a voting session and they rejected this proposal. So the EIP process stays in exactly the same state as I described in the previous slide. Here is this proposal, and you can see the reasons for why they rejected it. Оставь это пока. I would like to add that there is a security consideration section, security consideration section in every EIP. However, the text of the proposal is only submitted by the creator of the proposal. So if the creator of the proposal does not want to add the description of some issue for some reason, it will not be added. And there is no one responsible for adding it, even if the issue is known. So if the creator of the proposal does not want to include some security disclosure or security consideration in the description of his proposal, he can just ignore it. And we are left with the process where no one is responsible for this. Now I would like to highlight some takeaways from this discussion. So first of all, you need to understand that the security considerations of the EIP is subjective opinion of the EIP creator, and it is never complete because it only reflects the state of the issue at the time of when it was in last call, and after it got finalized, no new disclosures are added to the security consideration section, so it is never complete. The default implementation of ERC-20 standard is not secure, and it will inevitably result in a loss of money for your customers. So, for example, if you will just take the code which is in the Open Zeppelins repository and you will start using it, your customers will lose money in exactly the same way as I described in the beginning of the presentation. There are some possibilities of mitigating this problem. For example, you can restrict the logic of transfer function. You can apply a modification which will prevent tokens from being deposited on smart contracts with this function because it is not built for this purpose. But this will make your token implementation incompatible with some smart contracts which may for some reason expect tokens to be deposited with transfer function. For example, the Uniswap version 3, the router contract, if I remember correctly, it sends tokens with a transfer function. So you need to understand this. And also, like 90 or 80% of cases where people are losing money with ERC-20 standard are related to users depositing their tokens to the exact same contract of a token. The user can deposit USDT to the USDT smart contract. And the USDT smart contract is not designed to deal with tokens. It is designed to be the token. Likely with USDT, you can just contact the teaser company, they can destroy the tokens on their contract address and they can recover it. But some other tokens can do the same, and you will just effectively lose your money. So you can prevent users from sending tokens to the exact same address of the token contract that you are deploying. And this will solve like 80% of the issues that your customers may expect. The third point, every contract must assume that it can receive ERC-20 tokens, and it must implement a function to extract them. Because even if your contract is not designed to receive any tokens, there is just no way to prevent tokens from being sent to this contract on your end. And as a result, it is recommended to implement an extraction function. There are alternative standards, and I would like to highlight the ERC-223 token standard, which was created in 2017 to solve this exact problem. However, there are any alternative standards, and most notably ERC-777, ERC-1363, ERC-1155, and I would like to highlight that there is absolutely no possibility of designing a backwards compatible standard which would be secure. So it is impossible to solve this issue of ERC-20 standard without overriding the logic of how its transfer function works. So any standard which declares that it is backwards compatible with ERC-20 is insecure. At this point, I think that I covered most of the problems available. And thank you for your attention. If you have any questions, feel free to ask.